I am going to discuss depth first search in this video. This DFS, depth first search, is another search algorithm for traversing or searching tree or graph data structures. Unlike BFS, this DFS explores as far as possible along each branch before backtracking. It means that it traverses through one entire branch of tree or graph before moving on to the next branch. And this DFS is similar to the pre-order traversal, and it uses the stack data structure or recursion. If you take BFS, it used queue data structure to implement, but here the DFS uses the stack data structure to implement. So, we all know about the stack. The stack is the first and last out data structure. This is how the stack data structure would look like. So, the element which came first, for example, element 5 is there, the element 5 was inserted, pushed into the stack first, and then I am pushing the element 2 inside the stack, into the stack. So, now the one which came first, so when it comes to, like, according to the stack data structure, the element which came first would be coming out last, and the element which came last would be coming out first. So, we call it as last in first out data structure. Why? Because both the insertion as well as deletion could be performed only through one end when it comes to the stack data structure, whereas in queue data structure the insertion would be performed at one end and the deletion would be performed from another end. So, it is a first in first out data structure, but here in the stack the one which came first would be going out last. So, we call it as the last in first out data structure. Why? Because both insertions and deletion, pushing and popping, would be performed through only one end here in the stack data structure. So, here in the DFS is also going to use the stack data structure. Let us see how the DFS works on it on the given example. So, this is the example tree given, and it has 10 vertices. The total number of vertices here in this example tree is 10. Let us start solving it now. It uses stack data structure. We create one stack now. The stack is created. Parallelly, we are supposed to write the order in which the vertices are visited. Once visited, we are supposed to register it here. Okay. It can start from any vertex. So, here in the tree the root node is clearly given, it is 1. So, first it would visit vertex 1. Once visited, we are supposed to write it under vertex visited and explore next. So, if you explore one in BFS, like if you want to visit one, if you want to explore one, we would be exploring the one completely and we would visit both the node 2 as well as 3. Whereas here in DFS, like it will take one particular node and it will explore it. It would visit one vertex, explore it completely, and then only it would move on to the next node, next branch. So, that is why we call it as a depth first search. So, it would complete the entire left subtree first and then only it would move on to the right subtree, right. So, we visited the node 1. If you check one, either if you explore the node 1, either it can move on to the vertex 2, otherwise it can move on to vertex 3. So, you can prefer any one branch only, either the left branch as well as the right branch. So, here I am going to prefer, after exploring the node 1, I am going to visit the vertex 2. Since I have explored, the node 2 is visited, under vertex visited I am going to write 2, and once the node is explored, once the new vertex is visited, you are supposed to check the predecessor of the new vertex visited. So, 2 is the new vertex which I have visited. You check the predecessor of 2, the parent of 2, which is 1. So, that 1 you are supposed to push it inside the stack. But there in DFS, once the node is visited, all the visited nodes we would be inserting into the queue, but here once visited, the predecessor should be inserted into the stack data structure in depth first search. So, 1 is explored, the node 2 is newly visited, under the vertex visited have included 2, and also the predecessor of 2 has been pushed into the stack. And then again the current node is 2, I am going to explore the node 2. Again, if you explore the node 2, since I have chosen the left side, you can explore, like if you explore the node 2, you have to visit the node 4 only, because the left child of the vertex 2 is going to be 4. So, if I explore, I would visit the vertex 4. So, under vertex visited, write 4, and the predecessor of the newly visited vertex is 2. I am going to push 2 into the stack. and then again the current new node is 4. So try exploring the node 4. If I explore the node 4, it would visit the new vertex which is 8, write it under vertex visited, and the predecessor of 4 should be written, should be pushed into the stack. Next 8 must be explored, so I will try exploring the node 8, but there are no new vertex found under the node 8. So since there are no new vertex under the node 8, it is supposed to perform the backtracking. So where it has to go? It has to go to, since there are no option under 8, it has to find out some other option. So it has to move back to the previous level and it will look for any other option. So how it will move back, like how the code knows that which is going to be the previous node. So for that purpose only we are using the stack data structure. So you look at the stack top element. The stack top element is 4, right, which means that we are supposed to move back to the vertex 4 and look for other possible options other than this 8. Under the vertex 4 there was 8, so the 8 doesn't have any child node, so no other option. It has to move back to the previous state and look for any other option other than 8. So you just pop out the top element, pop out the top element from the stack. So now if you check, if you look into the stack, there are only 2 elements into the stack, 1 and 2, because 4 has been popped out, which means that we are supposed to move back, perform backtracking to the previous node. From the node 4 you check any other possibilities are there from the node 4? No, only 8 is the child node, there is no other child node for the vertex 4. So 4 also cannot be explored, which means that again you have to perform backtracking to the previous node. So which is the previous node? Look at the stack. The stack top element is what? The stack top element is 2. So pop out from the stack and perform backtracking to the node, to the vertex 2. Okay, look for another option, the alternate option other than 4 under the 2. Yes, there is another vertex is there under the node 2, which is 5. So it would be visiting the new vertex, that is 5. Since I have visited new vertex, under the vertex visited I am including the vertex 5, and also the new vertex has been visited. Check the predecessor of the newly visited vertex, which is 2. So push the vertex 2 inside the stack again, because we explored the vertex 2 newly and we have visited a new vertex. Once the vertex is visited newly, we are supposed to push the predecessor of it into the stack. So the predecessor to the node 5 is 2 only, so I have pushed into the stack. Now again try to explore 5. So if you try exploring the node 5, there are no new vertices are found. So the next step is no other option, we have to perform backtracking. So you have to backtrack to, look at the stack top element, the stack top element is 2. So pop out from the stack and perform backtracking to the vertex 2. And look for alternate option other than 4 and 5 under the vertex 2. There are no other options under the 2, which means that again we are supposed to perform the backtracking to its previous node from 2. So look at the stack, there is only one element in the stack and that is going to be the top element, that is 1, which means we are supposed to perform backtracking to the node 1. Check one other than this 2, any other alternate option is there? Yes. Other than 2 there is 3 also, that is the right child. So it would visit newly the right child, the right vertex, which is 3. So I have visited one new vertex, write it under here under the vertex visited, and since I visited this new vertex I am supposed to write the predecessor of 3 into the stack. So push the predecessor of 3, which is 1, into the stack. Now if you look at the stack, there is only one element in the stack, that is going to be the stack top element, and the next step is explore this 3. If I explore this 3, so first, see here we are exploring the left branch first and then only we are moving on to the right branch. So if I explore 3, I would go to 6 first. So 6 is newly visited vertex. So once visited, the predecessor of the vertex 6 is 3. So push the vertex 3 into the stack. Then again try exploring the node 6. So if I explore the node 6, the new vertex we would get 9. So the vertex visited is 9 and predecessor to 9 is 6, because the 6 is already explored. Push 6 into the stack. Then explore 9. If I explore 9, there is only one vertex, which is 10, which is newly visited vertex. So include it under vertex visited, and also the predecessor of 10 must be pushed into the stack. Then again try exploring the node 10, but we can't explore the node 10 because the 10 doesn't have any child node, which means we are supposed to perform backtracking. Backtrack it to the stack top element. The stack top element is 9. So pop out from the stack, pop out the 9 from the stack, perform backtracking to the node 9 and check, look for alternate option other than 10 under 9. There is no other option, which means again perform backtracking. Perform backtracking to the next stack top element 6. Pop out from the stack 6, perform backtracking to the node 6. Look for alternate option other than 9 under 6. There is no other option under 6. So again we have to perform backtracking. The stack top element is 3. Pop out this 3 out of the stack, backtrack to the vertex 3. You just look out for any other alternate option x other than 6. Yes, it is there. The new vertex is 7, which means the new vertex 7 is visited. So include it under vertex visited, and the predecessor of the 7 must be included into the stack. Try exploring the 7. There is no option, there are no child nodes for 7, which means perform backtracking. The stack top element is 3. So pop out from the stack, perform backtracking to the previous node. So then again try exploring the node 3. Is there any other option are there for the node 3 other than 6 and 7? No. So again we have to, since there are no other options, we are supposed to perform backtracking again. So backtrack to the stack top element. So if you look at the stack, there is only one element, which is the top element, that is 1. So backtrack to 1. Now look for any other option other than 2 and 3 under 1. No. There are no other option, there are no other new vertex to be explored, which means that we have visited all the vertices, and also if you look at the stack is completely empty. So finally, whichever the data structure you are using, for BFS we would use the queue data structure. So at the end the queue must be empty. Same even here in DFS also, the data structure must be empty. So if you look at the stack data structure, it is empty, and if you look at the tree, like if you look at the vertex visited, yes, we have visited all the vertices. Means the DFS technique is successfully applied here on the given example. Now let us discuss the time complexity. Here the time complexity of DFS depends on the data structure used to implement it. So when implemented using recursion or a stack, the time complexity here is, we got is, the actual time complexity of DFS is big O of V plus E. So V is the vertices visited and E is going to be the edges. So here again visiting each vertex takes constant time, and each edge also takes constant time here. For BFS also the time complexity is big O of V plus E, and here in DFS also the time complexity is V plus E. So visiting all vertices takes big O of V time. When it comes to applications, let us discuss few applications where this DFS can be applied. One is topological sorting. So this DFS can be used to perform a topological sorting of a directed acyclic graph. The second application is detecting cycles in a graph. It can help, this DFS can help in determining whether a graph has cycles. That is second application. And the third one is maybe for finding strongly connected components in a graph. So the third application is finding strongly connected components in a graph. So these are the some example applications, and we can apply this DFS on many more applications, many more domains as well. So in summary, the choice between BFS, because we discussed both BFS as well as DFS, the BFS was discussed in the previous video. So the choice between BFS and DFS depends on the specific requirements of the problem and the structure of the graph or tree being traversed. So this is how the DFS works, and in the next video let's discuss the difference between the BFS as well as the DFS. Thank you.